Good morning, students. Hope you have completed all your work which was given in the previous session, and we'll have a very small recap of what we have completed in the previous session. Like Sumati ma'am introduced about the metallurgy, and then what is a mineral and a ore, differences between mineral and ore, types of ores, and then different steps in the metallurgical process, then different type of concentrations. And this she just gave you an introduction and explained about the gravity separation and froth flotation. Now we are going to continue the lesson. We are going to continue with leaching process. First of all, what is leaching? So leaching, mainly that you know that the first step is the crushing of the ore. Now the ore is crushed and it is ready for the next stage. And in the next stage, we are going to learn about the leaching process. That means the ore is going to be dissolved in a suitable solvent, and that will be converted into a complex, or it can be converted into a soluble salt. So during this leaching process, the crushed ore is made to convert into a soluble salt or a soluble complex. And this is done by using one solvent, and that solvent will decide the type of leaching. Now that solvent, based on the type of the solvent, the leaching process can be classified as cyanide leaching, ammonia leaching, alkali leaching and acid leaching. Now we are going to just see in detail about cyanide leaching. See, what is cyanide leaching? Now, from the heading, you can identify that the cyanide used here is the solvent. Okay, so this cyanide leaching is very important, and it is mainly used for the extraction of gold and silver by a process called MacArthur Forest cyanide process. And here there are two main steps. What are the steps? First step, you are going to take the crushed ore and it will be allowed to react with a dilute solution of cyanide, maybe a sodium or a potassium cyanide. This will convert the metal into a soluble cyanide complex. Then what happens to the gangue? The gangue will be converted into an insoluble part, and here in this case it will be remaining as an insoluble aluminosilicate. Now you can see the equation. I've given the equation here for gold, and the same equation by replacing AU, you can have an AG and you can write it for silver. And the equation can be written for any, that is a general metal, also by having a symbol M. Now your soluble cyanide complex is ready. Moving on to the second step, we are going to recover the metal from the complex by a process called reduction. And all of you know what is reduction is that there is a decrease in oxidation number here. So in the soluble cyanide complex, you have a metal with a positive oxidation number, and it will be converted to the metal with a zero oxidation state, that is that original elemental state of the metal. And this is just obtained by making the soluble cyanide complex to react with zinc. And this process is explained by the name called as cementation. And you have the equation here, and see, you can see number of formula here written in square brackets. Hope you recall what you have learned in your detection and estimation lesson. So these are called as coordination complexes. And anyway, you will be learning about the naming of the complexes and in detail about these type of complexes in the lesson coordination chemistry later. So now moving on to the second type of leaching, ammonia leaching. When I say ammonia leaching, ammonia, that aqueous ammonia remains the solvent here. So you can take the crushed ore, example, you can take a nickel or a copper or a cobalt ore, and it is made to react with aqueous ammonia under pressure. So these metals can be converted into the respective complexes, and insoluble gangue, that is the gangue will be remaining as an insoluble part. What are the gangue you can have here is ferric oxide, ferric hydroxide and then aluminosilicates. How the metals will be converted? Nickel can be converted into this type of nickel amine complex, and naming can be done later. Okay, then copper can be converted to a tetramine complex, and cobalt can be converted to a pentamine aqua complex. So in ammonia leaching, what you are going to just remember is that you can have these examples of metal which can be converted into the respective complexes. The third type of leaching, which is called as alkali leaching. And this alkali leaching here, alkali, aqueous alkali is used as a solvent. The main thing and the important process which is related to this alkali leaching is that obtaining alumina from bauxite. And that process is referred as Bayer's process. And we are going to have what is the reason behind why we are going to extract alumina from bauxite, and why we are going to use this leaching process from bauxite is that we are going to make use of the amphibolic nature of bauxite. So it is going to allow to react with the alkali and maintaining at a temperature of 400 to 500 Kelvin and 35 atmospheric pressure. You'll get a soluble sodium aluminate, and you have the equation for that. And the impurities here are iron oxide, silica, and titanium oxide. And this soluble sodium aluminate obtained from the first step is just neutralized by passing through carbon dioxide, and in this reaction the soluble aluminosilicate can be, I'm sorry, soluble sodium aluminate can be converted into anhydrated alumina. And already you should have learned that tabular column which is given in the textbook, that is a different type of ores. In that you know the bauxite formula, and this Al2O3 XH2O, specifically 2H2O, and it is formed as a precipitate, and it is filtered, and the precipitate is heated about 1670 Kelvin to get the pure alumina Al2O3. Now we are going to move on to the fourth leaching process, that is called as acid leaching. Here acid leaching name itself tells you that you are going to use acid as a solvent here. So it is mainly suitable for sulfide ores. Already we have seen a concentration process which is suitable for a sulfide ore, that is the froth flotation process. Now here we are going to take an insoluble sulfide ore, and it is allowed to react with hot aqueous sulfuric acid, and it will be converted to a soluble sulfate along with an elemental sulfur formed. You can see the equation, it is given for zinc sulfide, that is the zinc blende ore, and this zinc blend is made to react with aqueous sulfuric acid, so it is converted to soluble zinc sulfate and elemental sulfur. So now we have seen four different type of leaching. What are the different type of leaching? Or cyanide leaching, then ammonia leaching, and then you have alkali leaching, and then acid leaching. Finally, last type of concentration we are going to have, and it is a different one, that is the due to the magnetic nature we are going to see this called as a magnetic separation. And this is mainly employed not only to separate the gang, it can be used for two things. Number one is that you can just use a magnetic, it is used to remove magnetic impurity from non-magnetic ore, as well as magnetic ore from non-magnetic impurity. That means it is able to just that is mainly it is helping to separate the magnetic part from a non-magnetic one. So how it is done is you are going to just take a crushed ore, and it is allowed to fall through hooper, and you will have a conveyor belt moving through two rollers, and out of the two rollers one of which is a magnetic one. And when you are allowed to fall, when you are just allowing the crushed ore to fall in this, what happens is whatever is the magnetic particle, if the ore is magnetic or the impurity is magnetic, that will be attracted towards the magnetic field, and it will be formed as a separate heap. You can refer the diagram for this from the textbook, and it is available. After you just watch the video, you can just see your textbook, and you can just see the diagram. That is, the textbook is the PDF which we have sent to you. And one of the examples you can have here is separation of magnetic impurities from non-magnetic ore, and separation of magnetic ore from non-magnetic impurities. Now we are going to proceed into the next step. That is the third step of metallurgical process, extraction of crude metal. So the previous step we have concentrated the ore, and now that ore can be converted into a crude metal by following two steps. Step number one will be the concentrated ore will be converted into their oxide form, and the next step will be the reduction of the oxide to the metal, that is the metal in their zero oxidation state elemental form. So here a major thing is involved, that is the principles of thermodynamic, which will be dealt later in the next session by Sumati ma'am. Okay, now we are going to see about the first step. That is, the concentrated ore has to be converted into the oxide form of the metal. And here, this can be done in two ways, one by roasting and the other one by calcination. What is the basic difference between these two is, this is decided based on the type of the ore. In case if the ore is a sulfide ore, then the roasting can be preferred and mainly suitable for sulfide ore. And this roasting is generally done in a laboratory furnace, and it is done in an excess supply of air. What do you mean by that is, we are going to take the concentrated ore and it is heated in an excess supply of air, and this is the major key point in roasting. And it should be maintained at a temperature below the melting point of the metal. And what happens here is that the concentrated mass, when you are heating it and it is done in an excess supply of air, that mass becomes porous, and whatever impurities present are converted into their volatile oxides. Similarly, the concentrated ore is oxidized and it will be converted into the respective oxide. And I have written only one equation for this, and remaining equations you have in your text, and which can be taken down later in the classwork. And now the second, what is that? The second way of converting an concentrated ore into an oxide. What is that? It is called calcination. And here calcination is mainly suitable if the ore is a carbonate or a hydrated ore. You all know what is a carbonate ore, like calcium carbonate, CaCO3, like that. And what is a hydrated ore is that if the ore is having water molecular crystallization, that is a hydrated ore. And here it can be strongly, the concentrated ore can be strongly heated in two ways. It can be heated in the absence of air or otherwise in the limited supply of air. This is depending on the situation. And whatever impurities present, once again here they are converted into volatile oxides. And in this case the organic impurities are also removed. And if the ore is a hydrated oxide, that is a hydrated ore like Fe2O3 3H2O, the water molecules, when you heat it, when you do the calcination process, the water molecules are removed in the as moisture form. So Fe2O3 3H2O, it will be forming Fe2O3 plus 3H2O. And if you have chosen a carbonate ore, then what happens is that then it will be converted into an oxide and carbon dioxide is expelled. This is a very normal reaction you should have seen with respect to calcium carbonate many times. And now we are proceeding to the second step. So what we have seen till now is that the extraction process, that is the third step of extraction, that is converting the concentrated ore into crude metal, which can be done in two steps. Number one is converting into an oxide, which we have seen that the concentrated ore can be converted into oxide either by calcination or by roasting. The step two will be reduction of the metal oxides. That means the metal oxides are reduced to the crude metal. And this is mainly done by a process we usually call it as smelting. And this smelting process, we are going to add two things along with the concentrated ore. One is a flux and another one is a reducing agent. First, let us see what is a flux. A flux can be acidic or basic. So which decides that the flux should be acidic or it should be basic is that the flux is decided mainly based on the nature of the gang. If the gang is acidic, then the flux will be basic. If the gang is basic, then the flux will be acidic. Now, what is the next thing? Why we are adding the flux is that the flux is added for two important reasons. One reason is that to remove the gang. So the flux will react with the gang and it will be converted into something called as slag. Flux plus gang, it will be forming slag, and the slag is a fusible matter. And the next thing is that the flux will reduce the melting point and it increases the electrical conductivity of the metal. So these are the two reasons why we are adding flux. Flux can be acidic or basic. As I told you already, that's decided based on the nature of gang, and they can be just reacting to form the slag. And the slag obtained in each and every extraction process, it can be reused actually, depending on its nature. So you can, if silicate slag is obtained, it can be used for making glass like that, and so on. Even sometimes if you are getting some slag, which is you think as a useless one, that can also be used for laying roads like that. Now, what is a reducing agent? Because in the reduction process, we are adding two things. One is the flux, which we have seen already, and now it is a reducing agent. This reducing agent can be either a carbon monoxide, or aluminium. And what happens in the smelting process? You take the metal oxide and then the reducing agent and then the flux, and it is heated at an elevated temperature, and you will get a crude metal. We are going to see a few examples for this. First example will be iron oxide. This iron oxide can be converted into iron using carbon monoxide, and here calcium oxide is used as a flux, which is basic, as the SiO2 gang is acidic. Okay, so let me repeat. The first example is converting ferric oxide into Fe, iron. And here carbon monoxide is used as a reducing agent, and we are taking calcium oxide as a flux, and it is a basic in nature, and as the gang is acidic, that is silica. When you just made these flux and gang react, it will be converted into a slag called calcium silicate. Now we are proceeding with the next example, which is called as the extraction of copper from copper pyrites. What do you mean by copper pyrite? It is a mixed sulfide ore. That means you have a cuprous sulfide and a ferrous sulfide combination. CuFeS2 is the formula. And first it is concentrated by froth flotation process. The reason is that it's a sulfide ore. Then it is heated in a laboratory furnace where the smelting takes place, and where the copper pyrites are first split up into the respective sulfides, that is FeS and Cu2S, and later on the FeS can be oxidized to form FeO. This FeO will react with silica and it will be just removed as slag iron silicate. And now the second step. So now at the end of the smelting process, what we are going to get in, that is during the extraction of copper, is that we'll get a slag, which is iron silicate, and we will also get a mixture of two things, mixture of metal sulfides, cuprous and ferrous, and that is called as matte. And this matte is then separated from the slag and it is taken into the Bessemer converter, and this iron sulfide present is further converted into iron oxide and it is removed as slag. The remaining copper sulfide is converted into copper oxide and then into copper. There is a small mistake here. This is Cu2O. I have written Cu2S, please correct it. The solid metallic copper obtained during this process is called blistered copper. Why it is called blistered copper is that the blisters appear on the solid part of the copper. The reason is that due to the evolution of sulfur dioxide. So you will get a solid metallic copper and it will be having blisters on it. The reason of appearance of blisters is due to the evolution of SO2 gas. That's why it's called as blistered copper. So kindly note here, the first equation, it should be 2Cu2O. And now moving on to other type of reductions, which we are going to see. Now we are going to see about the reduction of the oxide by means of using hydrogen. So this is mainly applicable for oxides which is having a very low electropositive character compared to hydrogen. So the metal oxide is made to react with hydrogen and it will be converted to metal. As you all know, addition of hydrogen is nothing but reduction. And it can also be done by means of using a water gas, which you have already learnt in S block lesson, which is a combination, a mixture of hydrogen and carbon monoxide. Nickel oxide can be converted to nickel by means of using this mixture, that is carbon monoxide and hydrogen. In between I have left out the reduction by carbon. Let me do that also. Reduction by carbon. So oxide ore can be reduced to the metal by means of just reacting with the coal, that is the coke, and it is heated strongly. So when it is reacting with the coke and it is heated strongly, you will get the metal, and it is done in a blast furnace. This is not done for metals which is converted into carbides. This is done only for metals which do not form carbides at its reduction temperature. So the zinc oxide can react with carbon so that it can form zinc and carbon monoxide. And the next one is reduction by metal. That is, you have the oxide form of the metal, and it will be made to react with another metal so that it will be converted to the metallic form. This reaction is simply a redox reaction. We are going to use few metals like sodium, potassium and calcium. The reason for using these metals because they can easily be oxidized, therefore they act as a very good reducing agent. So titanium oxide react with magnesium so that it converts itself to titanium and magnesium oxide is formed. So you can very easily infer from this that titanium oxide is undergoing reduction to form titanium and magnesium is undergoing oxidation. That's what we call it as reduction of metal oxides using metals. And in this we have the next part as the metallic oxides can be converted to metal by means of using aluminium. This is called as aluminothermite process. And these metallic oxides, like what I have given here, chromic oxide, Cr2O3. This chromic oxide can be converted to chromium using aluminium. It is not only for chromic oxide, you can also just use this method for Fe2O3. What is the meaning? Why it is called aluminothermite is that we are using aluminium, that is one thing, and another one, it involves a very high temperature condition. And what is happening here as such is you are going to take chromic oxide and you are going to have aluminium, and both of them is taken in a fire clay crucible. Crucible is something which can withstand a high temperature. And along with that, you are going to add an ignition mixture. The mainly a mixture added here to just bring out the process. That means it provides a necessary heat for the further reaction. And what is the ignition mixture is magnesium and barium peroxide, and barium peroxide is converted to barium oxide, once again a redox type of reaction. And now this reaction, barium peroxide and magnesium forming barium oxide and magnesium oxide, is a exothermic process. That means it provides an energy of 852 kilojoule per mole, and it gives a very high temperature condition, which will further improve or otherwise further help in the reduction of chromic oxide. That chromic oxide, aluminium, and this temperature which I have written here, that is a triangle symbol which indicates a very high temperature, is obtained from this reaction so that it will be converted to chromium and aluminum. This process is called aluminothermite process. Now the last one called auto reduction. The auto reduction says that there is no need of any reducing agent. It takes automatically. That means during the roasting process itself, it will be converted to the metal. You can have the example of this ore that is called as cinnabar, HGS. So it is a just concentrated and it is allowed to undergo roasting process. Finally, it will be converted to the metal. So now we'll just conclude this session, and I have not given any homework for you, but you are supposed to copy all these things in your classwork along with the other examples which is provided in the textbook. Because some places I have not given all the examples, I have taken one or two only. And after this, after the auto reduction, now the 3 steps of metallurgy process is over. That is crushing, concentration, and then this extraction of the crude metal. The next one is the refining, and in between that we are very much interested in a topic called as the thermodynamic principles involved in metallurgy. And this is mainly the major part of the lesson. The new concepts which you are going to see, it will be done by Sumati ma'am in the next class. And this thermodynamic principles help you not only in selecting the reducing agent, it also just infers that the reduction of metal oxide to metal is more easier compared to any other conversion of, that is any other compound converted into a metal. And the selection of the reducing agent, everything will be explained by ma'am in the next session. Hope you have followed, and I want you to just watch this video fully and take down everything in the class. So you can also take it down later on, because along with the video I'm also providing you a PDF of all these written materials, so that after watching the video you can take it down in the classwork and you please start learning the lesson, because this lesson will be tested and you will be taking the marks for an internal assessment. Okay, thank you so much.